Hello, chemistry people. This is Chapter 12, Lecture 3. This will be the third and final lecture for Chapter 12. We are going to be in the book starting on page 404, and this lecture is about the ideal gas law. So the equation that you need to memorize is PV is equal to nRT. All right. Some people call that PV NERT. Some people call it some other things. But you got to memorize it. Pressure is P, volume is V, temperature is T, N is moles, all right, because M was taken. So N is moles. R is the ideal gas constant, 0.0821. You do not have to memorize that. The units are important, though. Liters times atmospheres over moles times Kelvin, because it tells you that the volume has to be in liters, the pressure has to be in atmosphere, temperature has to be in Kelvin. So the unit can be very helpful on that one. So let's look on page 404 at on your own problem number 8. So it says, how many liters does 1 mole of an ideal gas occupy at STP? All right, so you know this is an ideal gas law problem because there isn't a before and after situation like there is with the combined gas law. It just wants to know how many liters. Okay, so we are solving for volume. So let's bring P underneath nRT. We would have volume is equal to nRT over P. So at STP, right, standard temperature and pressure, you know that the temperature is equal to 273.15 Kelvin. And you know the pressure is equal to 1 atmosphere. So our volume is going to be 1 mole. That was given in the problem. A lot of times you have to calculate that, but not in this case. R is our constant, 0.0821. Temperature, 273.15 K. And then our pressure is 1 atmosphere. All right, so if you put that in your calculator, you should get 22.4 liters. So give that a try and make sure that you can work that formula in your calculator. All right, pause the video if you need to, and we'll do the next 2 problems. All right, 12.9. So flip over a few pages in your book to page 408. So this is the very last page in the chapter. All right, and this is a little bit longer on the reading part, but not a hard problem. It says, in an automobile engine, gasoline, an important component of which is octane, is burned to make gaseous carbon dioxide and water. A gallon of octane has a mass of about 3,200 grams. If a gallon of octane is burned in excess oxygen, pressure 1 atmosphere, temperature 180 degrees C, how many liters of CO2 are produced? The unbalanced chemical equation is C8H18 plus O2 makes CO2 plus H2O. All right, so we've got to, this is going to take us back all the way back to chapter 4 with our balancing skills. C8H18 plus O2. We're not going to worry about the phases. This is the gas chapter. CO2 plus H2O. All right, and I said we weren't going to worry about the phases, and then of course I put it in. All right, so we need to balance. So I've got 8 carbons here, so I'm going to put an 8 right there. 18 hydrogens, we've got 2 here, so let's put a 9. We've got 16 plus 9, 25 oxygens, so we're going to put a 25 halves in front. And now we'll multiply everything through by 2. Okay, so I'll just go ahead and put a 2 there. 25, 16, and 18. All right, so I'm going to circle those just to make sure I don't accidentally use these coefficients. Okay, we have that. Now it says, now we want to list what we know. We want to know how many liters of CO2 are produced. So we're trying to figure out how many liters. So we're trying to get the volumes. It says that we have 3,200 grams of octane. So let's write that in, 3,200 grams. All right, I know on the CO2, just reading the problem, that the pressure is 1 atmosphere. So I suggest you just write down what you know in these problems. We know that the temperature is 180 degrees C. Going to have to change that to Kelvin. We know R is 0.0821. We'll put the units in later. For now, I'm just going to leave that. We don't know the moles. All right, and that 180 degrees C, that's going to be, let's see, 473.15 minus 2, so 453.15 Kelvin. I'll just go ahead and make that change now. All right, I can't get the volume yet until I get moles, but since I know we have 3,200 grams of octane, I can get moles of CO2. All right, so let's go through the stoichiometric process. We have 3,200 grams of C8H18 over 1. We want to change that to moles. If we add up C8H18 from the periodic table, it weighs 114 grams. And now we want to go to moles of CO2. And we want to cancel out or get rid of moles of C8H18. Now we get these numbers from the stoichiometric coefficient. So in front of CO2 is 16. In front of octane is 2. So when you put that through your calculator, you get 224.6 moles of CO2. All right, so now we can use the ideal gas equation. If we have PV is equal to nRT, we want to know volume, so that's going to be nRT over P. The moles we just figured out, 224.6. R is 0.0821. And our temperature is 453.15 Kelvin. Don't forget to change that to Kelvin. And the pressure is 1 atmosphere. All right, so running that through the old calculator, you'll get a volume of 8,356 liters. So the key to this, of course, you have to have a balanced chemical equation. Usually it's given to you balanced. The key to this is writing down what you know, and it's always going to be of your PV equals nRT, you're going to get 4 of those and solve for the 5th. Okay, so you're going to have 4 of these 5. You might have to use stoichiometry to get moles, all right, which we had to do, but you're going to have 4 of these 5, and then you solve for the unknown, which in this case was volume. All right, let's do one more. And that will finish up chapter 12. Okay, this is page 408 again. Okay, this time we have our chemical equation is carbon monoxide plus hydrogen. That yields CH4O. All right, and this is already balanced for us. Let's write down what we know. We have 500 liters. Just be reading along. I won't read this problem to you. But we have 500 liters of hydrogen gas. All right. And it's at STP. How many grams of CH4O? All right, if it's at STP, we know the temperature is 273.15. We know that R is 0.0821. We know that the pressure, since it's at STP, is 1 atmosphere. We don't know moles, but if we get moles for hydrogen, then we can get grams of CH4O. So, whereas the last one, we did our stoichiometry first, and then we used the PV equals nRT. This time we're going to use PV equals nRT first, and then go to the stoichiometry. So, rearranging this equation, we would say that N is equal to PV over RT. So it's going to be 1 atmosphere. Volume is 500 liters. Has to be in liters. If you're given milliliters, you got to change it to liters, because this equation, this ideal gas law constant, has liters in the unit. 0.0821, right, is our ideal gas constant. And then the temperature is standard temperature, 273.15 Kelvin. All right, plug that into the old calculator. You should get 22.3 moles. Now that's moles of H2. Moles of H2, 22.3. We want to convert that to grams of CH4O. So this is where we use our stoichiometric process. So we have 22.3 moles of H2. We want to go to moles of CH4O. Get rid of moles of H2. Using our stoichiometry, we'd have 1 to 2. And then finally, grams of CH4O. Going to get rid of moles of CH4O. 1 always goes by the mole when you have different units and moles are involved. Grams, it's going to be 12 plus 4 is 16, plus another 16 for oxygen is 32. All right, so 22.3 divided by 2 times 32 will give you 356.8 grams of CH4O. All right, that does it for chapter 12. The homework assignment for this particular lecture is practice problems from page 416, and you can work 8 through 10. All right, that does it, and I will talk to you next video.